And I guess I got to pick up the pace and get off free base. I mean, just pick up the pace a little bit here. So, uh, what problem did I leave you guys with last time? Do you remember something about balls and bins? Uh, what 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 was the issue?
It was the pepper problem.
The pepper, right? But I thought there was a balls and bins problem that we didn't do. That I had said, hey, something to consider, something to struggle with. Um, that I'm looking at it. Let me write it down here. So how many ways? How many ways to avoid this flare? How many ways to place? How many balls was this? 5 balls into 4 distinct bins. Okay, that's bins. How many ways to place 5 balls into 4 distinct bins? Hard stuff, right? So you notice that there's something missing there after the word place. So what's with it? What's with that? By the way, thank you guys for coming and being prompt. I've got 32 people. When we do distribute the test, or I post up the test, and you guys form your groups, uh, I just a warning: don't allow somebody to be in your group if they're not attending, okay? Because you'll end up having to spend a lot of your energy explaining what what's happening to that person that's not been attending, instead of actually working on the test. So I just want to. You might say, why would somebody not attend? Well, there's always somebody that thinks they're smarter than everybody else, and they can just read the book. That's a common one. I'll just read the book. I'll just read the book. No, you can't just read the book, because this isn't in the book. And the book is written at so many different levels. It's like it's got the super easy problems, got the super hard ones, it's got the impossible ones. The book is written for a big audience, people of all different levels. They could use the book in Harvard for all I know. I wouldn't be surprised. Or they could use it at Santa Monica College. I don't know. Okay, that didn't help. I've still got 32 people. And I'm trying to squeeze one more person, because we have 38 enrolled. And I'm trying to get, let me just check my computer for a second. Yeah, just like clockwork, they can't find can somebody do me a favor? I don't know. Let me try to send them the invitation. I mean, I don't know why they don't have it, but they don't have it. Sorry about that, but it's just a problem that some people may have added the course really late, late, and they don't even have the syllabus. Okay, how many ways to place them? What's missing in that gap between the word place and the number 5? 5 balls into 4 distinct. So what could go in that gap? What could go in that gap there?
word unique?
Say again?
The word unique or
Yeah, right. Or distinct, 5 distinct balls or distinguishable. You know, somebody said, when is exam 1? I haven't, the syllabus gives a general date, right? When, you know, if you look at this, the pacing guide, it'll sort of say when it, you know, when I give it out, I still have to get through chapter 1. So, but it's coming up. It's definitely come up, and I'll try to, I haven't specified exactly, but the syllabus says what we have, you know, basically, we got to do chapter 1 and chapter 2, so it can't be immediate. It can't be immediate. But I'll get it in your hands fairly, you know, it'll be fairly soon. Okay, so if we didn't write anything there, you might assume that those balls were indistinguishable. So if the balls are indistinguishable, how do we answer this question? So what does that mean if the balls are indistinguishable? How many bins do we have? 4? Here are the 4 bins. And you're trying to put 5 balls in there. Well, you know, it doesn't really, 4, 5. Okay, so this would be one possible way to do it. Okay, so there's one ball. We're not saying which ball that is, but one of them landed here, 3 here, 1 here, and none here. Okay, so that's one way of interpreting the problem where the balls are indistinguishable. I mean, if you wanted to make it sure that people understand, you could say, how many ways could you assign 5 people to 4 distinct tasks? And so 2 people could do the same task, right? So in that case, people are distinct, so that would be different. It would matter, you know, which guys are these 3 here. But if it doesn't matter which ball goes where, how do I solve this problem? It's a tricky question, but you have to have known, you have to have read chapter 1 and been to the last 2 lectures.
Would it be 4 out of 5?
Well, okay, we're going to say to place. How did I write it like this? To place, how many ways to place? I should have put the 5 here. So 5 identical or indistinguishable balls into 4. So if you don't put anything there, if you don't put the unique, you assume that they're indistinguishable, right? So let's see. Now, okay. So what did you guys say to do? I solve this sentence. So how do we answer this question in this case? You guys said it 3 people at once, but I think you're all right. Go ahead, say it.
4 to the 5th.
No, we're assuming they're not distinct. Just if you don't see distinct, you assume that the balls are identical. So how many ways can we place the 5 in here? So, but you don't distinguish between, you know, whether that was ball 1 or ball 2 or 3 or something like that. No, just those are just balls in there. How many ways can they be distributed? Well, remember this formula? And what's that supposed to equal? Somebody said that, I can see their sound was off, but they said it went like this. 5, right?
5.
Yeah, that's right. So 5. So what was the formula then? What was the formula?
If it's indistinguishable, would it be like 5 factorial over 4? Was it 4 distinctments?
Well, no, I'm actually appealing to a formula. So, okay, I'm appealing to a formula we had to generate.
Is
kind of
n
hard.
plus r minus 1, choose r minus 1.
Right. So it's n plus r minus 1, choose r minus 1. So this is the formula, right? So I'm appealing to this formula is hard to come up with, by the way. It's not easy. So, but now that we got it, we'll just keep it and not reprove it every time we encounter it. So what would the n be in this case? N is the total number of balls. So in this case, how many balls?
5.
So 5, and then what's r?
4.
And I don't know, what's the answer to this? It's what? 8, choose what? But I don't know what 8, choose 3 is. I should have calculated it before. In my notes last night, I was tired. I was on a work stoppage last night. But anyhow, what is 8, choose 3? Does anybody know it? times 6 over what? Over 6? 56? All right. Okay, so that's how you answer the question if it's phrased that way. But what if these are like people, these balls, you're distinct? That's gonna be harder, okay? Okay? I'm going kind of fast over this because it's a review of, this type of, this formula. It's solving integer. We're looking for the number of integer solutions to this. These are non-negative. It could be 0. In that case, n sub 4 was 0. Okay, so what do we do if we have distinct balls? It's like assigning people to different tasks or venues or something. You've got this 5 people and you want to assign them. How many different ways could that happen? Okay, so if you have the distinct, I think you guys were right about the answer because you were saying that it was what? Each person has 4 choices, right, of where they're going to go, right? So I think somebody said it. Go ahead and say it again. What was the answer
4
to
to
it?
the 5.
Exactly. Very good. Thank you for obviously staying in touch with the material that we did in the last week. That's good. But how do we twist this to make it harder? How did we twist
Have
it?
like exactly two empty bins.
I thought, okay, maybe my memory is, did we say exactly one empty bin? I thought we said,
We
if
did
it's
2.
2, then I apologize for being not prepared, but I thought it was with exactly 1 empty bin, the statement.
Well, we originally did 2 empty. What was the harder one we did? The exactly 1 empty was the one that we left on the table. We didn't cancel.
Good. Thank you. Now I'm remembering. At my age, it's not a given. Okay, now I'm remembering. So I modified this. So let's read it again. How many ways to place 5 distinct balls into 4 distinct bins, leaving exactly 1 bin empty? Now, I gotta be honest with you guys, okay? This is more of a computer science kind of problem, but it's not easy. Stuff in computer science is not easy, guys. I mean, I've discovered that there's a lot of hard. Now, this is a hard question. How do we do this? And if we do it, how can we be certain that we have the right answer? I made this up. I didn't get it out of a book. I don't have an answer. We could write, theoretically, we could write a computer program to go count all the possibilities, and that would make us feel a lot better about our answer. But that's not really what we want to teach her. Of course, we want to work through them, manually or by hand with their minds and try to anticipate formulas that way, or trends or something. Or we'll get some powerful technique later, and then we'll know, well, we did this problem by hand, and the powerful technique gives me the same answer. We can say no two consecutive balls leave 1 empty space. Let me try how I looked at this last night or the night before. So let me try to explain how I do these or try to do them. So I look at the result of the distribution as a vector. Okay, as a vector. So again, we have 4 bins. Okay, and what are we saying here? What is the assumption?
Exactly 1 bin is empty.
Right. So exactly 1 empty bin. So maybe it's bin 1 that's going to be empty, right? There'll be nada in there. So if you just talk about exactly 1 empty bin, so that would mean that what? That the distributions would be coming out of if there's no 1, then you have 2s, 3s, and 4s, right? It would be looking at the case of 2s, 3s, and 4s. It'd be the only numbers you'd have in the vector. But there's something, to review this, let's take a look at this word right here. Exactly one empty bin. That means that if we counted a case where there were 2 empty bins, say just 2s and 3s were used, that would be not, you're not supposed to count that. You'd be over counting. So again, realize that we don't have a textbook with an answer at our fingertips. There's probably a formula we can look up on the web if we're so inclined. If we ask the check tutors, they probably would say, we're not going to do it, or they'll pretend, they just won't do it because it's not a standard problem. But let's start figuring out what the formula would be to get the answer. So let's avoid this this glare here. So let's figure this out. So how many ways could we exclude one number from the vectors?
Or
Four,
choose
right?
one.
Well, there's 4 different ways. We could either, one could be the one that doesn't show, or it could be 2, 3, or 4, right? So there's 4 ways. Is that okay? Or did I say, did you misunderstand? I'm just curious. Why did you say 1?
I said 4, choose one.
Oh, sorry, I didn't hear it. Sorry, I apologize about that. Okay. Somebody asked something. 4 choose recovered combinations. Yeah. We can say no to, yeah, okay. Let's try to get an answer first and see if we can do a different one. Okay, so amongst these 3 now, how many ways, if we're just using those 3, how many ways, I know we're going to overcount, but how many choices do I have for the first ball that goes out? It could be what? It could go into which bins? Ball number 1. It could go into 2, 3, or 4, right? Here, here, or here. So how many choices is that? It's 3, right?
3, and then
So-
there's 5 balls, so 3 to the 5th.
Yeah, exactly, but we have overcounted, right?
Yeah.
So let's take the low-hanging fruit. Let's get rid of those cases where you would get and so 2 empty bins. So in other words, forget about this. We're just in this situation. We're looking at this right now. Okay, we're looking just at this portion because that's not going to happen. So those cases where all you get is all of them in 2, all of them in 3, or all of them in 4. How many cases is that? Because overall, then you'd have 3 empty bins. You don't want that. Now the tricky part is when you have 2 empty bins. I want to get rid of those possibilities. So how many ways could I end up with? In other words, 2 empty bins all around. So let me check it. So I have 3 here. So to get 2 empty bins all around, I'm going to have an empty one here. So that means one of these numbers is not going to show. Besides 1, of the 2s, 3s, and 4s, one of them won't show. So one of these will be empty. Exactly one will be empty. I'm trying to take out that possibility. So how many possibilities? So there's, say that you're not going to have any 4s, so have 2s and 3s. How many ways can you do that? Well, you have to exclude one of these. So there's 3 ways to do that. There's 3 ways to exclude, and then say I'm not going to have any 4s. So how many ways for 2s and 3s? Well, there's the same reasoning that went before. It's 2 to the 5th, but you want to eliminate the case where it's just 2s and just 3s. Let me see what that adds up to. Okay, I'm not going to do all the arithmetic, but I get 600 out of this.
Professor, would
Yes.
you be able to explain one more time how you got the -3?
Right here?
Yes.
Okay, that shouldn't be too bad. This is harder. The -3 are the cases where you're going to get 2 empty bins over here. So 2 empty bins means they're all 2s, or all 3s, or all 4s. In other words, you don't have any 1s, but I'm getting rid of the case where it would all be twos. You know, because that's definitely not exactly what we already got so you want to make sure that twos, threes, and fours that all show up. There's no empty frames on this. So a case would be like we want to eliminate this possibility, or if they're all threes or all fours. And there's three cases of that.
Okay.
Because
And
right
then-
now, you're 3 to the 5th, right? Definitely this would be one of those cases, right? All twos,
Yes.
or all fours, or all threes. But what else do we have? This is the harder one. What's happening here? We're trying to get rid of the cases where not one of the numbers doesn't show. Okay? So there's another number that, say, twos don't show, right? So there's 3 ways that you could select a number that doesn't show, but then you have just two numbers. Like this would be a case of 3s and 4s, right? So you get 3s and 4s, your 3s and 4s, and that's no good because the end result will be 2 empty bins there, right? So you get rid of those, but then that overcounts. You want to be able to take off the cases where it's all 3s or all 4s, and that's why there's a -2 right there. So this counts the cases where it's exactly 2. And this is exactly 3 empty, exactly 2 empty. It's complicated, okay? There's no question in my mind it's complicated, okay? But I kind of, if we're persistent with this type of problem, we can master it. Okay, so let's look at a modification of this problem.
Would you actually just go back real quick and explain again the last portion of what cases were the underlined in red?
Yeah.
What
Okay.
cases are those?
Okay, so we're trying to, this section right here is supposed to get rid of those cases that were counted here where you have exactly 2 empty bins altogether, which means that we know we got one already gone, right? You're not going to have any one. Bin 1 is going to be empty, but then there's going to be another empty bin. So there's 3 ways to choose which one of those bins is going to be the next empty bin to make 2 empty bins total.
Okay.
I wish there was an easier way to do this or a different way, but I can't think of it at the moment. So if I find it, I'll share with you. But it's also the time thing. We should probably. Okay. The thing about counting is you never want to overcount or undercount, but overcounting tends to be the norm. When I notice it's sort of a difficult problem, the tendency is to overcount. And what was hard about this was exactly 1 bin empty. That was hard. Okay, let's just take let's do something a little different. Okay, a little bit. It's something a little creative that I can use for the test. Let's count something different. So this is about POSIX. It should have been covered in 320 and 326, so I'm not even going to ask you if you did it or not. But so if you have 3 numbers, how many arrangements are possible? Well, I've got 3 numbers, say they're distinct numbers. So how many arrangements? We kind of know that, right? You could, from smaller to smallest to largest, it's possible. We don't know what order these numbers are in, but there's lots of arrangements possible here. B, C, A, B, A, C, C, A, B, C, B, A. There's 6. Okay? If there's no restriction on this, there's 6. Is that clear? So that's just counting arrangements. Potential arrangements. If you're putting them from smallest to largest, we don't know which one's smallest, which one's in the middle, which one's larger. So these are all potential arrangements of those if they're placed in order, okay? Now the poset thing comes into play here. So if you say in addition that this information, this is something that you have, how many possible arrangements, sorted orders are there for these numbers given this condition? So what does that condition mean? Does anybody want to take a guess? If you write, this is called a poset or a Hasse diagram, not to be confused with a Hesse diagram. That's a whole different, it's philosophy, not Hasse diagram. But what do you think this means? This means that A is bigger than B, A is bigger than C, but you have no other information than that. I know I'm going kind of fast here, but I want to generate a problem that's not in the book, and it ain't in Chegg, and you know what I mean. I got to be creative. You know, if you can't do it, then I'm not supposed to be teaching you guys. So,
Does
well,
that mean like A has to come before?
no, let's put the bigger on top, okay? So A is bigger than B, A is bigger than C.
Okay, so like we're retaining the shape. Like I'm not sure what
What we're trying to do, we're trying to find how many sorted orders are consistent with this condition. So you could have, what could we have here? So A is bigger, so A would have to come at the end. If these numbers were in sorted order, so is there possible sorted orders? Okay.
Would it just be 2?
Say again?
Because since A would, if we are assuming A is greater, that A only has 1 factorial ways to be sorted, and then B and C, assuming they're less, would have 2 factorial ways to be
Right.
sorted.
Right. So let's put down those results. So it could be B, C, A, or C, B, A. So the answer is what? You're right, correct. So these are the only sorted orders that are consistent with this additional constraint here. Now, some people might look at this, if they've never seen posets before, they didn't take 320 from a reputable teacher. No, sorry, I didn't say that. You know, but if you didn't get that, just because these are on the same level doesn't mean you don't know which one's bigger than the other. Okay, there has to be a line going down from one to the other to establish their relative order. Okay, that's the story. So this is kind of not a whole lot of constraint. It just puts A as the largest, but B and C could be B could be bigger than C or vice versa. Okay, all right. Okay, let me see if you understand what I'm doing, because what is this over here? There was no poset with this, so any of these orders are consistent. There's no constraint here, so any order is consistent. You know, with you don't have any constraints, so it could be any of those. That's why that was 6. Okay. Okay, so let's modify things a little bit. So.
I have a question. In terms of when you were explaining just the order of how many arrangements we could make of letter A, B, and C, you were showing us the permutations for it, right?
Yes, but
And
those
then-
are numbers. We're assuming they're numbers. So
Okay.
what we're looking at is potential orders, from sorted orders from smallest to largest,
Mhm.
right? So
Okay.
these are numbers, distinct numbers, right?
Mhm.
We don't know which one's biggest and which one's smallest, right?
Mhm.
So
Okay.
all of these are possible. You know, all of them are possible. We're looking at possibilities. We're counting possibilities. So if you have 3 numbers, there's 6 ways that they could be placed in. You know, they could, if you put them in sorted order, it could be one of 6 ways. You know, But let me give you another problem, and this maybe will make it more clear. So let me erase that. Let's. What if the poset is this? A is bigger than B, and we don't have any control on C. So, what are the possibilities here that would be consistent with this poset? Let's write down the possible sorted orders. What could they be? Well, you tell me. So you start.
BAC,
Okay, so which one? B,
BAC,
B, A, C. Very good. That's one of them.
BCA,
Yes.
CBA.
Any more? Is that it? Are you guys okay with this? All of these are consistent with this information right here. Okay, so B has to be less than A, but that's true here, right? In all of these cases. Okay. So you see where I'm going with this. This can get a little more complicated. Let's go. Suppose we have 4 numbers.
You said B has to be less than A?
B is less than A, right?
Okay.
Right. So this is when you do sorted orders. Usually you go smallest to largest. I mean that's sort of convention in computer science. Do you see how these are consistent? So this is the total number of possibilities.
Yes.
Okay, good. Let's make this a little more complicated. What if I have 4? Okay. This is an A here. And this is a little more complicated. So this case, A, B, and C, D. So now the additional information from the posets is going to be this. All right. Okay. Does anybody want to hazard a guess on this one? How many ways this could happen? Just it's okay if it's a wild guess, but what do you think the number is going to be?
Four.
Yeah, 4 sortable ways.
If you're right, I'm impressed. Let's start doing. Let's enumerate. Okay. So we have to sort of count something. Somebody wrote something on the chat. From my iPad to direct 64. Well, careful. There are 64 different ways to write it in order, right? But some of those would not be consistent with this because this is saying you have to have B less than A. You have to have D less than C, right? So it can't be all of them, right? Because whatever the B shows up, the A has to be after it in the sorted order.
I'm gonna take a wild guess and say 8.
Well, let's try to list them out. So help me out here. So you can go B what?
BDAC.
And then DC, right? Could you go B,
BD.
D,
AC.
AC, or how about B, or even BD what? BDCA? Do we got them all, or am I missing one here? What if I start with D? How about D, C, BA, right? How about D, B, AC, or DBCA? I don't know. Did I miss one? Can you think of another one? What do we have here? So D, so BD, so D.
Professor, would one of them be DCAB?
Well, remember, B has to come before A.
Oh, right.
But I don't know. You're thinking DC. Why can't DC? But if you do DC, you have to go BA after that. Do you see how this gets to be a game? You know, it becomes sort of, you know what I mean? It starts to become, okay, we really have to count this stuff. Right now, it looks like there are 6 possibilities. Okay, so I think that's the correct answer. But you know, this is the sort of thing where if it's a take-home test, what do you think I'm going to do? I'm going to make it a little more 6. Right? AIM is AIM. I don't know if I'm pronouncing it right.
Yeah,
But
AIM.
that's. Did I do it right?
Mhm.
Okay.
Correct.
Yeah. Good. I think you're right. So how do I make this? How do we make this into an exam problem? Because we try to build the test beforehand, so you guys see what's coming. Well, you know, you're gonna it's just how do you increase the complexity with something like this?
You can make 2 of them independent. Or
Well, you
Increase the alphabet
you could
size.
use more. You could use more numbers, right? So you could go A, B, C, D, E, F, And you could do something interesting here. You could make one second now, A, B, C, D, so E, F. You could do something like that, and you could play the same game, So relative to that post set, now how many? Give me one. Just give me one ordering that would be consistent with this post set. Just give
D,
me one. Go
D,
ahead.
B, C, F, A, E.
E, C, F, yeah.
B,
What?
B,
B.
A, E.
Very good. How many are there?
lot.
I know you don't know, but I just want to take a wild guess, Okay, I'll leave that for you guys. People say there's no homework here. What's so weird? Yeah, you got this to do for homework. If you're having trouble following me, come to my office hours tonight at 6:30. So we'll just keep going on this. I don't know the answer to this. That's why I haven't worked it out yet. But I want somebody. Do you want to hazard a guess? Just a ballpark guess. This is putting quite a bit of constraint on the possibilities, is it not? Because if you didn't have that, you'd have 6 factorial, which is how big?
Maybe
7.
like 9.
It's 720, right?
Yeah.
But D would always have to be first, and it's either A or E is last.
I don't know. Does D have to be first?
E just has to come before C.
I mean, let me
you're
try.
right, yeah.
Let me try one where D doesn't come first. What if I go BF first? BF, D, C, A, E. Isn't that good?
Yeah. Yeah.
I think it's that, because we don't know where these are. A lot of people look at these CASA diagrams and they see the B and the F are on the same level. And they think it's like water, water finds its own level. No.
But you could
You
draw
don't
the
really know
line
the
even
relation.
longer down if you wanted to.
Okay, say again.
You could draw the line from A to really far down below D. Visualize that
Oh.
B could be less than B.
Oh, yeah, right. Yeah, I mean, don't write this in there, but I think what you're saying is,
Yeah, just for visualization.
yeah, it's possible. All right, you guys, let's just let's cover the multinomial coefficient thing really quick here and try to understand what situation that applies to. I realize I'm jumping around, but that's what it is. It's like a grab bag of techniques that Ross is presenting to us in the first chapter, and it's all valid. Believe me, you will need these later on. So multinomial coefficient. Okay, first of all, logically I should talk about binomial coefficients, but I'm assuming you know that from a pre-calc course or something like that. So binomial coefficient, what is that? Well, if you take x plus y to the n, what's the formula for that? 0 less than equal to k less than equal to n. What is it? It's n choose k times x to the n minus k times y to the k. It's just what's useful about this is you don't have to multiply everything out. You don't have to go on a distributive law nightmare, trying to, or what do you call it? So you don't have to use the FOIL method until you're blue in the face. You have a compact formula for this. And these, even if you're not concerned about that, these are very interesting, these binomial coefficients, and they come up a lot. So this is the binomial formula, and you can prove it. In the book, they have different proofs of it. So, I mean, do you want to check it to see if it really works? I mean, I don't want to do it, take the time, but I mean, what is this? What is that? Okay, so
X
let's apply the formula here. So it looks like what's the first term? X squared
squared plus 2xy
plus 2 then the next term, so what is n in this case? So n is 2. So how many terms do I expect to get out of this? So I got the 0th term, k equals 0, k equals 1, and k equals 2. I get 3 things. So your binomial coefficient will be 2, choose 0, will be one of them. The next one is 2, choose 1. And the next one is 2, choose 2. So this is 1 by definition. 0 factorial is 1. 2, and this is 1. So 2x, both of these are 1. And then the next guy is what? Plus what? So it does what you expect it to do, you know. It collects terms of the same with the same power of x and power of y. But that's we know this from we should know this before. You know, if not, I strongly recommend you read the part in chapter 1 where they address this. But the multinomial coefficient, that is different. That is different. Okay, and that's what I want to look at right now. So not binomial, but multinomial. Okay, so let me try to tell you where this comes from. If you have n things and you want to distribute them, and these are distinct. So everything here is distinct. Everything. I don't know how to write properly. Distinct, everything. So distinct things into, I'm sorry, I'm trying to rush and I'm making a fool of myself. So everything is distinct. The things and where they're going, okay? And you want n things and you want to distribute into these you want to put n1, so n1 into this bin. So this is bin 1, you're going to put n1 in there, and bin 2, you're going to put n2, and bin k, you're going to put n sub k. And how many ways can you make the distribution? This is a very, very useful formula, just extremely useful. So, first of all, these guys, you have n things to distribute. Nothing is either created nor destroyed, at least not in this class, not nuclear chemistry. So the things distributed have to add up to how many you put out there in the first place. Does anybody know the formula for this or what the symbol is for this? So these numbers are set. You're going to put n1 in here, n2 and n2, n3, n sub k here. They're set. How many ways to do it? And you have a total here. So how many different ways to distribute these distinct things into these distinct bins? How many ways to do it?
I mean, I know the symbol for it looks kind of like a combination, but you have n on top, and then you list them on the bottom, n1, n2, n3,
Right.
n3.
Good. You had a good class in combinatorics. You
Yeah,
had a good class, and you remembered it too.
the bottom ones have to sum to n.
Yes. Right. But okay, so how to what's the formula? So I got a symbol here, but I don't know what to do with it. Well, you're actually going to do something really simple with it. You're going to take n factorial over n1 factorial times n2 factorial times nk factorial. That's what you're going to do there. So I don't like it when there aren't numbers involved. I mean, but I think this is such a powerful formula that you should have that formula in your mind. But I like numbers, okay? So there's an example in the book. And I'd like to let's just get, before I try to prove this, I know you're probably going to prove it with the time, but what's an example that we can write where, okay, so the example I want to write is from the book, and there's 3 bins. There's three they're actually job assignments to police officers, so they can either go street patrol, seat time, donut time. No, wait, street patrol, seat time are reserved, and you want to put put 5 in the first, 5 into this. So this was, what did they call it the first time? This is street patrol. And you want to put, you need to have 5 guys go that way. And seat time, whatever, seat time is 2. I guess that's office work. And the reserve, you want to put 3. And of course, how many officers do you have to get distributed here? As I forgot her name there. She said that it has to add up to N. AIM is your name.
Yes, that was me.
Okay, yeah, am I pronouncing that right?
Yeah.
Okay. So how many do we have to? So we have 10, right? So 10 have to be distributed, and these are people. So that matter. They're distinct. Of course, they're people. They're not. It's not like Star Wars where they have drone soldiers or something. They're all the same. So I want to get a number here. I want to know how many ways could we take those 10 officers and divvy them up so that 5 go into street patrol, 2 go into seat time, and 3 go into reserve. Wait, I'm sorry. Reserve. Okay, so what would the formula tell us? What would the symbol be here? So it'd be 10.
Would be 10 chooses 5, comma 2, comma.
Exactly. And what number is this going to be here? So it'd be 10 factorial over 5 factorial times 2 factorial times 3 factorial. Whatever that is. But we're using that formula, you know? We're using that formula. What's the number? I mean, I always like to get a number when I'm doing a problem. What is it? This is
2,500 and some. Oh, sorry. Thought you meant the other.
I think you're right. I think it's 2,500. I remember that. Is it? Is what you
Yeah,
got?
it's yeah.
I think
It's
you're right.
around that number.
I think you're right. Very easy. So it's a lot, you know. We only have 10 people. My gosh, you know, how do you get 2,500 possibilities? Well, these are distinct, you know, distinct people. So, but how does this formula come about? 2520. Ah, my bad. Okay, 2520. Thank you. How does it come about? So the way to think about it, sorry, I'm having to keep on erase what I have there before. But this is the picture, but then how is this formula justified? So where to write that down? So you have to choose, you had how many again? You had 10 altogether. You had to choose the 5 for the street patrol, okay? That's how many ways you could choose those guys for that. And then how many are left? So you've looking at all different ways. So you've chosen 5 for street patrol. How many officers are left?
We have 5 left, so to determine seat time, it's 5 choose 2.
Right. And then, you know, there's nothing you can do now because you have 3 left, but all 3 have to go into that place. And supposedly this is what? This is the 2520. But how does it tie into this, you know, why is it this? Okay, so my question is this is the formula, and here I just have a number. How do I get from that number? How does it relate to the formula? That's my question, okay?
Well, we could write down the formula for combinations.
Yes. That's right. So we can go what? What can we do? 10 factorial divided by 10 minus 5 factorial times 5 factorial times what? 5 factorial, 5 minus 2 factorial times 3 factorial times what? Essentially 1. What cancels here? Well, you see this, if you look at this, this is canceling with this, and this is 3 choose 3. So this is, this one here is 3 factorial over
Shouldn't it be
factorial times 3 factorial. So this is canceling with this. So how does it, do we reach that thing there? Right?
if I choose 2, shouldn't it be 2 factorial instead of 3 factorial?
5 minus 2 times 2 factorial, thank you. Uh-oh. Let's see what happened here. So 10 choose 5, so 5 times 5. Okay, the 10 factorial I'm good with. So it's a 5, okay, so let's make sure that I did this right. So 5 factorial, 5 minus 2 factorial times 2 factorial. What about this one right here? 3 factorial over 3 minus 3 factorial, 0 factorial. By the way, 0 factorial is 1. It's by convention. When you're added, what's 0 to the 0?
Also 1?
I think it's a controversy
Right.
about.
Yeah.
I think there's a controversy about what it's like an ongoing historical debate. But okay, so this 3 factorial here. So it's not with this, but this is canceling with this. So what remains here? So I see a 10 factorial, I see a 5 factorial. This is the 3 factorial, cancels with that. So what am I missing now? I have this 2 factorial.
You get this 3 factorial.
And because this cancels this, I still have this 3 factorial here. So that's the same as that formula on the any of the box. So it really it's just a consequence of using this the choose notation. Okay, so let me sag into the other thing I'm going to do here. Somebody put 6. I think that's an old one. Okay, any question on this? I'm sorry, I kind of dunked it up, but it's just things cancel. So when you analyze it this way, but why are these multiplied, by the way? Why don't I add them? Or sometimes people ask me, why are you multiplying those? Because those are different possibilities, right? The 5 officers, I mean, once they've been selected to go into the first category, then any change in the second one, you see, that's a totally different distribution. So it's like stages. You multiply the different stages to get the total number of different possible outcomes.
For this particular example, it's just basically showing us an extension of the binomial, and then what you're using is the basic principle to multiply them together to get the number of division of ways to
I did this mucking around kind of unsuccessfully, was to try to show you why it's true.
Okay.
But I'm okay if you just memorize the formula.
Okay.
You know, it's just, there'll be times when applying this formula will save you some steps, you know, in a more difficult problem.
But in a greater scheme, or should I say, in a more general sense, this problem is basically just showing us the number, or how to find the number of ways to divide, I'm going to say, things into distinct groups.
Yes, distinct things into distinct. But you see, the thing is that there's an additional constraint here. That's an excellent. I'm glad you brought this up. So there's something you're missing in what you're saying. It's distinct things into distinct groups, but what? What's the other condition? Let me ask that to everybody in the class. What's the other condition?
It has to be distinct objects or distinct things as well.
It is. These are people. They're distinct. So we're not doing the drones, in Star Wars. So these are distinct people, and those are distinct job assignments, right? Categories.
Mm-hmm.
So that's not the issue. There's something that you need to have about the problem to apply this formula. What is it?
The size of the groups is fixed?
Yes, the size of the groups is fixed. When we did the thing about the balls going into the bins, the bin 1 could have any number of balls, right? So we can't apply this formula to that situation when I started the lecture. Is everybody good on that? Are you? This formula is a very narrow applicability, right? But you have to specify the first group has 5. I said one. The first one is 5. Second one has size 2. And the third one has size 3. You've got to specify that.
Okay.
So I never, all this mucking around, I never gave you, we have the binomial theorem. We don't have the multinomial theorem. So I never use it, so I have to look here at my notes. Forgive me for that.
Isn't the theorem you actually just gave us, or AIM actually just gave us, the multinomial theorem?
No, those were the multinomial coefficients.
Oh, okay.
Those are the like, remember in the binomial theorem, you had those n choose k. Those are the binomial coefficients. But the theorem, the binomial theorem solves, it multiplies something out for you, right? So the multinomial theorem will multiply out something that's got more than 2 terms. So binomial is like bi is 2, so 2 terms. Multinomial is multi, so like 3 and up. Let me give you this example from the book. Just touch on it just for a second. Just for a second here. So example 5e. What we're supposed to do is multiply this out, okay? And using this multinomial theorem. So what happens is, how should I teach this? I probably should give you the theorem now. And I hate that, just doing it that way, but I think that's it. The actual theorem okay, so it goes like this. Hopefully I'm not in a washout for this. Let me check if I'm in a washout. I don't want to start underwater. Yeah, I guess I'm sort of. Okay, so x1 plus x2 plus xr. Sorry if that's hard to read, to the n. So this is a special case here. So here r is 3 and n is 2. So what does the theorem say? If you multiply this out and you get these multinomial coefficients. And we know how to evaluate this because we already did an example. I had factorial over the product of those factorials. And these variables will be to those powers. Okay. Now the thing that makes this interesting is not just the coefficients, but these numbers here. We know what they have to add up to. They have to add up to n, but you want that n1 plus n2 plus n sub r equals n. And these are non-negative integers. We have seen this before. So what can be said about this over here? So this will be a sum of a bunch of terms. What am I getting at here? Every term is one of those integer solutions to this equation, okay? Non-negative integer solutions. So if I was to ask you, if I apply this theorem to this special case, how many terms are there? How many terms are there? What would you say?
N plus R minus 1 R minus 1.
It's that stupid formula again. Exactly. So we would have to use the formula n plus r minus 1, choose r minus 1. Now we got to figure out what n is. Well, I'm looking at this right here. This will tell me the number of terms. So n is what in this case? 2, right? What's r? So I remember doing this, and I thought it was 12 terms. I don't know. Let's see. Six terms. It can't be 12. That's not a binomial coefficient. So it was 6 terms. How do I know that? So this is 5 minus 1. This is 4, choose 2. This is 6. So if we apply this formula here, I know from this counting thing that we developed in chapter 1 that there's going to be 6 terms. Could you write some of these terms? Could we write some of the terms? So let's use the power of eraser to bend this to our needs. So what's n in our case? So it's squared, right? So what are the possibilities to get those 6 terms? Well, what can we get? Let's do this. What would be the different possible? So what are the solutions? Just write down the solution to this. We can have what? So let's write down the solution. So what do we need? N1 plus N2 plus n3 equals n. So how many solutions are there to this? And this n here is a 2. Let's enumerate. What are they?
Like
Uh,
0, 0, 2.
Yes, 2, 0, 2, 0. Actually, you're supposed to do it in some order, but I don't care. So what else can we have? 0, 2, 0. What about 0, 0, 2? I've got half of them done, right? 1, 1, 0, 1, 0, 1, 0, 1, 1. I think that's all of them. So these would be these exponents, okay? Here. And this accounts for the 6 terms. Okay, I didn't do.
What
you know,
are
I
we
didn't do
solving
the.
the summation? I'm kind of lost.
Oh, what would it? Okay, what I'm doing is telling you what the different terms are going to be. There's going to be 6 terms. Each one will be one of these. So the summation is over all possible solutions to this equation, integral solutions.
Oh,
And we figured out there were 6. So this must have 6 terms. Would it have helped? I
brain
don't
turned
know.
off.
Would it have helped if I put vectors here? I don't know. Maybe I should just write in.
I wasn't. I guess I wasn't following from the. I must have missed something. I just don't know what problem we're solving.
Oh, we're trying to apply this formula to this, to how to expand this out.
Oh.
So the formula says you're going to have terms. You're going to have 6 terms because that's how many integral solutions there are here. And it tells you what the coefficient will be as well as what the powers are of your variables.
That's interesting.
So yeah, if you've never seen that before, it is interesting, right? Because I don't know if you were, my situation was when I was a student, if I saw this, I would have to multiply it out. You know, it would be a mess. How many terms would it have if I multiply it out?
5, 6, I don't know.
Well, potentially 9, right? I mean, if I do it without collecting the like terms, right? So, but yeah, I get it down to 6. So what is it? I mean, let's see. Let's actually do it. So let's look at these. Help me out here. So what is it going to be? Let's just write down the answer. So it says 2. What does that mean? If you have 2, 0, 0.
X to the 1 squared, right?
That's going to be x1 squared. Hold on a second. So that's what? It's 1. So, and there's no x2 and there's no x3. So I just hit this one, right? How about 0, 2, 0? What is that?
X2 squared, x3 squared.
Right. So I've got that. Let's see if I can
x1 times x2, I think.
Yeah, but okay, so what? Okay, let's look at this carefully. What is that coefficient associated with 1, 1, 0? So 2, 1, 1, 0. What's that equal to?
Oh.
What's the formula?
I still don't understand that notation.
Which one? This one?
Yeah.
Oh, okay. This notation just means 2 factorial over 1 factorial times 1 factorial times 0 factorial.
Oh, so it's kind of like choosing between 3 buckets, basically.
Yes.
Isn't that
3
the same
distinct
as that
buckets.
other problem we just looked at?
Right.
Okay.
Exactly. So there's 3 buckets, right? But you only have 2 things, so there's always going to be at least 1 empty bucket.
Yeah.
So if you're frustrated, you could always say, what is bucket?
The answer is 2.
Oh, 2, right. Okay, 2 times what, though? 2 times what?
X sub 1 times X sub 2.
Yeah, I think
Good.
so.
And now help me out, because I just did this. I need to do some other ones. How about this one?
That's 2 times X sub 1, X sub 3.
How about this?
And X sub 2, X sub 3.
Kind of right over here? No. Okay. Well, so there it is, using the formula. This is the perfect take-home kind of test problem because it takes forever to do. the tutors are not going to do it. Of course, you could probably just, if you have a graphing calculator or some software, whatever you have, you could just say, what is it? Expand out. Isn't there something like function? Yeah, you can expand out, right?
Okay, I think I get it.
I mean, you could reverse this, right? And say you had a particular problem. What is the coefficient of x2 times x3, the term x2, x2, x3? I mean, they can ask a question like that. Then you have to go back and figure out, well, let's see. And the answer is 2, but how do you know that, because it's a binomial, it's a multinomial coefficient.
Mm-hmm.
Okay, so having done all that boring stuff, yes, we did all the boring stuff. How much time do I got left? I got 9. Wait a second. What? I got 9 minutes. Okay, so let's do something interesting now. Okay, let's do something interesting. There's a super interesting problem in chapter 1. Does anybody know which one I'm thinking about?
Does it have to do with the tournament?
Tournaments, right? I like tournaments because I'm a sports fan. Okay. What kind of tournament is a knockout tournament? What's chaos stand for? Knockoff? No, knockout. What kind of tournament is a knockout tournament?
Boxing?
Hmm?
Boxing, maybe?
Okay, that you can get the knockout, but usually boxers don't do tournaments because if you know what I mean, it's pretty tough on your body to get punched in the kidneys.
Yeah, that's true.
I know in the Olympics they sort of do that, but I was thinking more like
If you're eliminated, or if you lose, you're eliminated from the tournament.
yes. So a second chance tournament would be like a double elimination. You got to lose twice, and you'd be surprised how many different tournament formats are possible. And it's a very interesting topic. If you're, how many people are sports fans out there? I mean, if you like, I like to watch tennis on TV, and they have this seating, and this, why they have seating? But you think about it, okay? Rhetorical question. But this question here is: you have 8 players, and say they're tennis players or something, and they ask a very interesting question. At least to me, this is very intriguing. A knockout tournament means, you lose once, you're gone. You're out of the tournament. Can anybody, suppose you had, 30 players in a tournament, and their prizes, significant prizes for first place, second place, and third place. Could it ever be the case that the tournament's unfair? In other words, the third best player did not walk home with this tournament, with this, his prize?
Yeah, because you're only paired up against a specific set of people. So
Right. So how is it that the third place guy could not wind up at the end with his third place trophy and his cash in his back pocket?
I don't know. I used to think about that a lot years ago, and now I don't remember how I figured that
I
out.
can give you a reason. Okay, so Lewis Carroll, I don't know if you know, he was a mathematician, besides a writer of kind of, I would call fantasy books or something, Alice in Wonderland. He, in 1882, he noticed this unfairness, and he said that the third place player might get knocked out of the tournament because it's a knockout tournament really early on and never have a chance to assert his skill. And how does that happen?
If he goes up against the first or the second place player.
Yes.
Early in the tournament, which
That's
is
right.
Possible from the random
That's right.
distribution.
Right. And that unfairness kind of rankled him.
Yeah.
Okay, I've got 5 minutes.
Maybe there should be no bronze trophy.
Well, yeah. Well, the thing is, the way they get around it, quote unquote, is with seeding. So they make sure they don't seed the 2 best players to begin with, because then that's second player's out, and it's unfortunate because whoever's going to get the second place not is going to be inferior to that guy who really was the second best. But anyhow, losers bracket. Do they have losers bracket in tennis? I don't know. I watched a lot of tennis. I thought if you lose, you lose. I mean, they have losers brackets in soccer. World Cup soccer. I didn't know they have, but I'll look it up. But anyhow, this question says how many tournament outcomes. Let's just put outcomes, okay? Let's make this simple. How many outcomes are possible? Your homework, by the way, is to read this, to do it, to understand it, okay? You have homework. Don't pretend like I haven't assigned anything. I want you to become a walking encyclopedia. I don't even know if the horse is. All I know is the horse is a horse, of course. No, I'm sorry. I wish I had time to talk about it, but I got to quickly pop this out here. That sounds interesting. 25 horses. Okay, how many outcomes are possible? Well, just look, we have limited time, right? Let's just nail out the first round. What does that look like? Just get a picture here. What's my first round going to look like? You understand here? These guys are going to play each other. They can't all play on the same court, so they have to be in different venues, right? There's different court, maybe even a different city. I don't know, just across the street or someone. So this is the issue here, right? So 4 venues. You got 8 players. You got to pair them up, and they're going to play each other. How many outcomes are possible?
Well, it's like a tree structure, so I wonder.
There's different outcomes that could happen.
Let's use what we know. Let's hit the multinomial. Let's hit that with that formula.
Oh.
Sorry, I'm rushing you guys, but I wouldn't normally teach. If this was one-on-one, I'm tutoring you guys, I would never go this fast, but I don't have a choice. So what's that formula for distributing 2 players here, 2 here, 2 here? These are different venues. What's that formula?
A chooses 2, 2, 2.
Good. Now that's assigning 2 players here, 2 players here, 2 players, and 2 players, right? But you know what? Does it really matter what venue they played in? It just matters who they played each other with, right? So I've got to divide by something to mod out or just to factor out. But it doesn't really, like these 2 players could have played in this venue or this or this. It doesn't matter. All I'm concerned about is who plays who. So what do I have to divide by here?
2?
Well, for every, say you've got players and they're already set in these venues, but you could do any permutation of the venues, right? Would not change the fact that those 2 players are playing each other. So how many permutations of the venues are there? Okay.
Oh,
Now we ain't done yet. Let me check the time. I'm probably out of time.
wait. I find that a bit confusing.
Well, this counts if the venues. See, you got 8 distinct players, right? No identical twins.
Oh, now I get it. I think.
These are different. It's counting the different venues, but that's an overcount because all I'm concerned about is who played who. Okay.
Okay.
Who plays who?
Well,
I don't care that
where
it's in
I find-
venue A or venue B,
Okay.
C, or D.
I guess what I forgot to think of is that the venues are stationary, but and then if
Yes,
Okay.
they are stationary.
and you could have the same 2 players go to a different venue, but
Yes.
they'd still be it
Playing each
doesn't
other,
matter
right.
what venue they're in.
Yes, yes.
Okay.
But I'm missing something. Let's close.
You're
Let's
also
close the
missing-
circle now.
I think
Because
you're also
we-
missing the players, like
Well,
at the
no, I've
venue.
got them in there. I've assigned them, right?
Yeah.
So we're talking about round 1 here. So we want to know what are the total number of outcomes for round 1, right? So outcomes means who got assigned to who, and also what? We've got to report back what?
Who won?
Ah, right. And how many different possibilities are there for win-loss on this? You got 2 players. Only one's going to win, right? There's no ties in tennis as far as I know. So how many different outcomes are possible in terms of who won and who lost?
2 per venue.
Right. Well, you got the venue. It's really 2 per match because we don't care
2
where
per
they're
match,
playing.
yeah.
So how many is that?
To
Aim, are you still there? It's gotten awfully quiet.
4 to the power of 2, so, or excuse me, 2 to the power of 4.
Yes,
think.
let me see if I lost somebody. I did, didn't I? Well, Aim's still there. Usually.
I'm sorry, I have a cat in my lap. I had to get up to unmute.
Okay. Okay. I was just worried about you. You know, I know
Yeah.
I'm going a little over, but I didn't want
So that,
to lose
that
you.
would
Well, I don't
be-
want to steal the show. Somebody else can do this one.
It's my party, and I'll cry if I want to. No, nobody would say that, right? No, I'm sorry, you guys. I'm just waiting for that. No, okay. No, I'm okay. You're not stealing the show. If you're not saying something, I'm afraid that something's wrong. You know what I'm doing? Okay, so we got to multiply by one, and let's just close the show down. What number is
wait,
that?
I'm still confused about, so all we care about is the who goes against who, but
Yes.
so we
Yes.
figured out the venues thing, but then isn't there also like redundancy with like what order the people are placed in? Like
No,
with-
because
like,
there are some. Here got 8 people, right? This is the way to match. This is to pair them up in different venues.
I get that, but then aren't they still ordered? Are we still counting? Aren't we still counting a match twice?
No, because this is the number of matches if you distinguish with venues. But if you put this in here, it doesn't matter which venue. It's the number. This is the number of matchups. This is the number of possible, winners and losers on those 4 matches.
Okay, I still just don't understand how we're not switching. Like, I thought that was counting like imagine.
Yeah, it
you
does.
have
This
those
part,
2 dots in one.
Yeah,
And
this part
then-
right here. Look, see this part? That counts. That counts. It
All of the
matches the
different
guys up,
ones.
and it also says which venue they're going to.
But then
you
I'm
see,
saying
when you
like
divide by
after
4 factorial, that removes the overcount, because it doesn't matter which venue they play, just as long as they played each other.
I know, but then what about the order in which, like, if you assign the same 2 people to one venue, you could assign one first and then another one second.
Oh, no.
Or you can
You
switch
don't, you don't care about that. It's just a pair. Just a pair.
That's what I'm saying. I thought we were counting that, and so don't we
No,
have to
no.
divide by
It's
2?
it's just these 2 guys go into this box.
Well, then how
Not
is
one
I
goes
don't
in and
understand
the other goes in.
math.
But
I
anyway, what's the
don't
answer? We
understand
gotta
how the
close-
numbers make sense.
What's the answer?
No clue.
What is it?
Let's see. Oh, we have sort of a duplicate there. It's gonna be like, yeah, it's gonna be that.
Okay, I got to be respectful because I'm over. I don't want that to happen because you guys got to get set up for your next class if you're taking one. I'll hang here a little bit, but Brandon wrote something, 8 total, 4 matches, 2 people per match, 4 winners. Exactly, that's a good summary. Does everybody see his post, his text, Brandon?
Ooh.
Brandon's. Now you can tell me what the 25 horses is. I know it's silly about it.
It's a interview question that concerns itself with trying to find the fastest 3 horses out of 25, but you can only race 5 of the horses at a time. So you want to make sure that the third fastest and second fastest don't get eliminated in rounds, because the third fastest overall may lose to the first fastest in that round
Mhm.
of 5 horses. But you don't want it to be eliminated too early. So how do you do that in the least number of steps possible?
Okay, can I just, I'm going to write that down, but I want to ask, does anybody have a question? I mean, we're done with the class, you guys can read through what I've covered and practice the examples in the book. And in Ross, there's one of the last problems has to do with fish. You'll know it has a star on it. Do that because it uses that n+r - 1, choose r-1 formula. So do that problem.
Are we on chapter 2 now, Professor?
No, this is still, believe it or not, it's still in chapter 1. It's a short chapter. It's got tons of good stuff in it.
Are we doing chapter 2 next week then?
I probably will start it, but I have to close off because I want to do a couple problems from the end of chapter 1. There's a good hearty list of problems. I want to do a few of those to get you guys aware of the level, in which the problems come in at.
Okay, thank you.
Yeah. keep reading that book. Well, I'll see you on Thursday, right? So you get any question on chapter 1, you ask me Thursday.
Professor, just a quick question. Not related to the topic. I'm actually from your 5 o'clock section. I just
Good.
came earlier.
Yeah.
So this is the same type of content that we'll be going over later, though, right? Just so.
Yeah, I'm going to repeat. As gruesome as it sounds, I have to do the same thing. What's the word for that? It's
Correct.
well, it's kind of like pushing a boulder up a hill, right? Continuously. What was the name of that Greek character?
Sisyphean?
Yeah, it doesn't look like a lot of fun, right?
Okay, so I don't have to worry about like different material or anything like that, right?
No. I mean, I just have to worry about maybe I'm getting old and demented and I can't remember what I did. That's the only problem. It'd be my fault, if I went off on a tangent, told a different joke.
Okay. All right. Thank you so much, Professor.
Okay.
Enjoy the rest of your day.
Yeah, thank you. You too. Thanks for coming early. Okay, so somebody wants to any question on this, or I kind of go to the horses problem? Any question?
No, we're good. Professor, before I go, I have a question too. Is it possible for the syllabus, because I was one of the students who joined kind of late to your class. Is it possible if you could send it?
Sure. Just what's your name?
Carlos Leon.
Okay. Could you email me, because I posted it up on Canvas, but you don't have access to Canvas right now, right?
I do, but it doesn't pop up the syllabus.
Oh, it's under announcements.
Oh, okay. Thank you very much.
I just use announcements. I don't do the
Got it. Thank you very much.
Sure. Let me get to. Okay, so guys, are you ready? So we look at the horse problem. Okay, so make this clear to me what the problem is. So you have 25 horses.
Yeah, there are 25 horses. What is the minimum number of races needed so that you can identify the fastest 3 horses?
Okay, hold on. I'm confused on what you just said. You mean in the worst case, the minimum number? So in other words, you're looking for an algorithm, basically, you're going to race horses, but you want the worst. You're trying to control the worst case, right?
Yes. Yeah. It's the minimum number of races. So you're trying to
in
find
any
the best,
case, the horses come to you in any order.
Exactly. So
okay,
you want to do the worst case.
Not the average case.
Yeah.
So minimum number of races, right? And number of races, and how many are in a race? 5?
You can race up to 5 horses at a time, but you cannot. You only can keep track of the order that they cross the line. There's no other metric that you can store. So you can't count the time it takes them to race or anything.
Okay, so when you say the order, that you be the
first, second, third across the line.
All the way down, like 4th and 5th.
Mm-hmm. Yeah.
Okay, so you can get. So basically, you sort. You're gonna sort. I'm gonna sort 5, right?
I actually have it up to class, but I can drop the link to the problem in the chat.
Oh man, I almost was gonna do it.
but I'm interested. I'll come by office hours.
Thanks,
and I'll
because
go over
I
this.
think I've got an idea. I think what happens to the races, you're actually sorting 5 of them.
It's weird, and you have to do some kind of bizarre graph grouping.
Yeah. Okay. But you want to do what? You want to find the top 3? Is that the?
Mm-hmm. Yeah, it's the fastest 3 horses.
Got it.
Okay. Thank you, Professor.
Great problem. Thank you. Okay, you guys. I think I'm ready to.
I think what you would do is just sort the 5 horses, and then eliminate the 2 worst ones, and then grab another 2 and sort the 5 again, and just keep doing that repeatedly. That's how I would do it anyway.
Well, let me do a picture for that. Okay. Do you have a moment?
A moment.
Are you good? Okay.
Yeah,
so
I'm good.
What I would do is I got 25, right?
Mm-hmm.